Okay, good evening everybody. My name's Chris Lambell from the Electrical Engineering Group for Engineering New Zealand. Just thought I'd do a quick run through upcoming events, a few other things, and we'll hand over to Bruce. So our next event is 28th July, that's 2 weeks time tomorrow. That's Helios talking on lightning protection, and that'll be a good one. The 11th of August, we've got Kane from Enesis talking on, I'll give an overview of battery technologies, and I've seen his presentation. That's another good one. It gives a good broad overview. And then, well, 2 weeks ago, we should have had Gallagher talking on electric locks and credential types, but unfortunately that got called off because of COVID. So Gallagher now coming back in on the 1st of September. So that's our next 3 events effectively. A few other notes I thought would be worth just mentioning while I'm talking. So in terms of lighting, we've had a few members requesting should we not be doing things on lighting? Should we not be partnering with the IS? Well, the good news is we are. We've had some discussion with Greg Williams, who's the president of the IS, Cedric Williams, not related by the way, is in the Wellington committee. So we're looking at setting up a collaborative technical society so we can share events, share knowledge, which I think is the right way forward because the lighting industry is such a compact part of New Zealand. It's better off being one body as opposed to just fragmenting it. So that'll bring up some new events and opportunities to collaborate. A few other things. There's a few people requesting a power engineering team or power engineering group, shall we say. Now, I'd like to think we are the power engineering group. Unfortunately, there's nobody on the committee or nobody's in the membership who has the time to put any events. And so if people want to see this group head more to the power side of things, then by all means, please contact me. We'll certainly give you the opportunity to do power-related presentations, power-related events. And that's the same with electronics. If anybody wants to talk on electronics or that side of things, then we can certainly give you a forum to do that. Or if you know people who want to speak, then I'm quite happy to organise them to speak. The problem I have is that being from a building services background, everybody I know predominantly works in building services. So I'll hand over to Bruce now. Bruce did this presentation to me probably 15, 16 years ago, and it was a good one. I'm not too sure if I've mastered it yet, or I'm still learning, but it is a good presentation. It's what I recall of it all that time ago. So I'll hand over to Bruce. Just a quick note, we'll do the presentation. We'll take questions at the end. Probably the easiest way. We'll take questions from in the room, pass the microphone around. Then we'll read out questions from people online, and the usual rules. These events are about sharing knowledge, not scoring points. So if any game playing, we'll draw that to an end quickly. And if anybody thinks they're better or knows more, then get in touch and you can do a presentation yourself. And that's a genuine request. But we are here as friends to share knowledge, not to score points. So that bombshell, hand over to you, Bruce.
Thank you very much, Chris. Can everybody hear me? Yeah, perfect. Well, thank you very much, Chris, for inviting me here today. I was quite excited about it because it's been quite some time before I've been in front of an audience and an online audience for that matter. 15 years seems like a very long time. You're still looking as young as I am, so that's a good sign, I think. But today I really wanted to go into quite a lot of depth around selectivity and cascading because as engineers, I think the key thing that you want to be able to achieve for your client is really reliability of the network. And to do that, you've got to have a full understanding of this. I'm going to take you back a little bit with stuff that you all probably know, but you may not know and you may pick up a few things. So I just think we need to go through a few terminologies around circuit breakers, understanding the things, because if you understand them, then when you're out in the field with the contractors that you're dealing with, which I'm sure you get a lot of queries from, the switchboard builders, etc., who typically know what they're doing as well, you have a lot of debate in that area. So understanding this area or the breakers themselves is very important. So selectivity and cascading is what we're talking about today. This works. I'm sorry to say, I'm just trying to, and technology is not turning it for me. Here we go, we're in business. It wouldn't be right if that didn't happen to me because it always happens to me, technology things. So here's what we're looking to go through. So short circuit fault currents, we need to understand that. That's the number one thing first. How do you analyze these things? That's the important thing of the network right from the get-go. The terminologies that you're going to be using are all the way through there. They are in the documents that you send out to your customers, to your clients, to the builders, etc. Getting that sort of information right or making it simpler for them is going to make the project go better. Low voltage circuit breaker settings. you really need to know this stuff. Selectivity, the curves, the tables, as you can see up on there, there's quite a lot to go through, but I think we'll have a good time doing it. So, low voltage protection plan. What's this? This is very important. This is your starting point for your customer. This is what you've really got to get your head around. So you'll see there 2 tiers, the customer needs and the protection plan. So the customer need is really what you're discussing with them, isn't it? You need to know what they want to achieve with this site. And a protection, you have to comply to the protection equipment, the equipment you need. Continuity of supply is the key element that you want to achieve, and the capex, that really you want to do it at a price. You're always going to be pushed to get the price down. How do you achieve this? Well, you can achieve it with a protection study as a starting point, a selectivity discrimination study, or a cascading, or all 3 together. I would typically say all 3 together. How are you going to do that? Who does this? Who supports you with this? Well, as a supplier, Schneider Electric, we want to support you through that area. So, yeah. Let's just take a step. This is really a thought-provoking slide that I wanted to discuss with you, and that is who has the idea of what to do? It's essential to know what to do, but who does? So if you don't know, you know where to go, which is obviously your supplier or your immediate superiors and so forth. But the reality is this slide is about who takes responsibility for the study. Is it the engineer? Is it the contractor? Is it the manufacturer? Is it the supplier? So we think it's us to support you, but we think the responsibility is out in the field. So it has to be really often the switchboard builder with the contractor with what you want as consulting engineers. So if you can make that happen, but we know that's a difficult area. It doesn't seem to fully work. What I will say is that I'm confident, and I see switchboard builders out there doing a really good job now where they're putting labels on their switchboards saying this is the short circuit fault, this is the way we want to, the switchboard is applying cascading to it. They're doing some smart ideas now in this area, which is good. And so they're labeling more. But at the end of the day, they do rely on the consulting engineer to come up with the design. So if you feel like that you can't fully do the design, how do you get around that? So we have tools that can guide you through this, but we also have people in the industry that can support you through it as well. So the switchboard builder, they know what they're doing, they know the product well, so rely on them. That's what I would say. Rely on them as much as you can. Yeah. This is, maybe it's your battery on this thing. Sorry, there we go. So let's start. This is a typical network. We've got levels of a system in here. Level 1, 2, 3, 4. 4 final distribution. That's all your miniature circuit breakers. Level 2 and 3 are molded case circuit breakers, ACBs, and sometimes the level 1 could be a higher level as well, or another level of ACB. So there is a lot there that you have to try and get right in your distribution network. And in terms of selectivity, or just, I keep on saying selectivity, but I need to say discrimination as well. It's a terminology that is being used more and more, and a lot of the literature is telling you it's selectivity. Okay, so you'll hear a bit of that as I go through. So the first thing you need to consider is what sort of faults are you going to deal with? Because not all projects are the same, but you typically will have overcurrent and you will have short circuit, but let's just have a look at what those faults could be. There can be earth leakage. I'm not going to look at this in this case. The reason why I put that up there though is in Europe, they do discrimination or selectivity in earth leakage because they apply it from the source all the way down to final distribution. They're very good at doing it. They know what they're doing with it. They have a different they have a different system that they operate on. Ours is a TNC, but they use IT. They have a lot of different systems there where earth leakage works better. We don't advocate as a company, even though we have earth leakage capability in our main breakers, ACBs, we don't advocate putting it in that area. Why? Because you don't put it in the sub-distribution and the final distribution. So if you're not doing that, you're opening yourself up to nuisance stripping, a real problem. So if you want earth leakage in, absolutely do it at final distribution, but beyond that, make sure that they're closed networks, okay? If they're not closed networks where you can control it, then I wouldn't bother. Circuit overcurrent fault, long time. So this is your typical one that you have. That's the major fault that you see out in the field. 130 to 150% could be less than that, but it's going to be around that 1.3. You might have heard that in the standard 1.3 times. So that's why I'm talking about 130 to 150% overcurrent, and it can take up to 1 to 2 hours on some of these protection devices before they trip, but they're in tripping zone at that point. And we as a company have circuit breakers will even give you a pre-alarm saying that you're in an overload state. So it's quite good. The technology has moved on a lot in that area. There's another one which is called inrush current. So nominal current rating could be 4 to 15 times. And I've made a note there, not a fault condition. Not a fault condition means is effectively you've got loads that have inrush currents. You don't want the breaker to trip. So you need to know where you need to set that at. And you've got to have the ability of a circuit breaker that can do that. So that's an important one. It's a fault that's there, but you don't want it to happen, but it can happen. And often if a breaker is happening around this type of fault, it's because the selectivity has not been done. Someone's just put the breakers in and they're all set to minimums and you've got a problem. Ground fault, another one. Often that is done separately, but it is more and more done in the breaker as well. And that's often around about 10% detected ground fault current. So, and you'll see to the right there, I put the international terms there, which is IR, IST, IG. These are IEC international terms. So you'll see those everywhere. You'll see them on breakers, so you know what they are. Arc fault, that's one of the worst ones. That's the short circuit. You're going to see 10 to 50% of the prospective fault. The prospective fault is your job or the engineer's job when you do the design with the software that you use. You're the one that's determining what that is. And the voltage short circuit is the worst one you can get. You can see 100% of the prospective fault level sometimes, but that's what you design the board on. You start from there. That's what we would expect you do, even though that's probably not the case. So determining the short circuit fault level. This is a nice little formula, which you've probably seen back in your engineering days, but it's still valid today. And you can see, and I'm not going to go in any great detail on all of it, but you can see this is the nominal rating here, current of the transformer. S is the kVA of the transformer times 10 to the power of 3, voltage and √3. And once you use that, so I'll move on to the next slide, you'll see this is what it can look like. Now, I've just also put in here a table that we have in our tech support technical pages in our catalogue, and you can get that in a lot of our catalogues. It's typical, so I'll just go through it. But this is based upon a 3-phase short circuit, voltage short circuit. So when you're starting your network and you're putting in your transformers, you've got 1, 2, 3, whatever. So here I've selected a 1 MVA transformer. The nominal rating of current that can get out of it is 30. Well, I know it's about more 1400 amps. Typically you get about 1400 on it. Amps, you might get more. The fault level, you'll know off the top of your head, is typically 27 kA. You get a couple of 1 MVAs together, you've got 55 kA. And this is the key point here. This is the impedance value of the transformer. That's what you need to know. And you can see it's here in part of the formula. But what we're saying is you need to get this information from the transformer manufacturer and get that data from him. That's your starting point. And of course, you've got other impedances in there. You've got the cable, you've got the bus bar, all that sort of thing. But we're not taking that into account. We're just saying, look, the transformer is feeding the switchboard, and we're saying the switchboard has got this sitting here. But we know it's going to be less, but so what? Let's start at that point. Because you know, excuse me, you know, a lot of the protection devices are well above this. They can deal with a lot more than this. So you know that's available from suppliers like ourselves. So this area here is really just showing you that we've only got one MVA on the previous one, but here we've got three together, three transformers, all connected. And each one of those has a circuit breaker on it, and that circuit breaker there has to withstand the potential of this, the fault level of that transformer. But if we have three of them, this circuit breaker has to be the sum of all of them. So we're looking at significant then. We're looking at a sizable fault level that is on this board if you've got that many. And then when we're calculating, whoops, I'll go back, when we're calculating the fault level and the devices around this area here, we have to also consider that you might have a bus coupler in here and you might have a generator. So we need to do the settings, and the protection calculations around a variety of different setups. We need to take that into account. Okay, terminologies. These are all pretty simple, and I don't need to go through them too much, but all I would say is that the nominal rated current of a circuit breaker is the starting point, IN. So that's the first thing you look at when you go to a breaker or you want to select one, that you need to know what the nominal rating is. And the overload protection, anything greater than 105, it's in an overload state. It's going to trip at some point, okay? Instantaneous. Earth fault between phases and earth can be up to 10 times the nominal rated current. Sizable. It's a major amount of current that these protection devices have to be able to withstand. Right. Terminology of overload and short circuit protection settings. There's a lot of settings on some trips, and there's not many on others. So long time protection, I mentioned IR. But there's also another one called TR, which is the time delay on the thermal setting. This here is invariably not used in the mid-range of the network, but is often used in the source breakers. But it's good to know that it's there. And so the x-axis in time and current here, you're actually adjusting the curve up, away from, and giving a little bit added time for the downstream breaker. It's not showing it in here. Downstream breaker, time to trip. So time in thermal is a rare thing used. So if it's sitting there, all I would suggest you do is, because you're not really using it, you can actually push it out high. There's no, or low. Low is actually better, to be honest, for the network. Short circuit protection, IM, and it's also known as ISD. So IM is magnetic protection. So there are different types of trip units. We'll talk about that in a minute. But the area there is often the IM and ISD settings are the ones that are often not set correctly. So whenever we see a circuit breaker, you go into a switchboard or you've designed something, that area there is often set either far too low or far too high. It's better to set it as tight as you can based upon what your prospective fault level could be. Don't always push it out, because if you're pushing it out, that means under fault conditions, it's going to see that it can potentially see a higher fault than it needs to. So all that connected equipment, cable, etc., is likely to be impaired at a greater current value than it needs to. Okay, so that setting there is important to get right. And then all breakers have instantaneous multi-case circuit breakers and ACBs all have instantaneous protection, but sometimes they don't have it as an adjustable element. It's just inbuilt in the breaker. And so it reaches a certain amount of current and the thing will go out. That's very important that breakers are able to do that. And then we have earth fault that can be added in some more advanced trip units. Okay. So I've brought this in, I've gone through these, but I just want to show you these three types of trips, just to give you an idea of difference and what the contractor is facing, what the switchboard builder is fine. Switchboard builder is dealing with this every day of the week, and he knows what he's looking at here. But a contractor, the first time's coming up there, you haven't done a protection study. You haven't prepared them to say, well, this is what we need to do, or you haven't said you must set this at this and this at this. So if you haven't done that, then it's ready for failure, isn't it? Right at the beginning, it's not a problem because you haven't got any loads connected or very few of them. But as time goes on, if these aren't set correctly, it is a problem. And often it always is in the early stages of the project. So this one here is what we call a thermal magnetic trip. And there is truckloads of those out in the field, more than anything else. And obviously all sorts of brands, obviously, you know, this is ours. But in here, this one's telling us that it will have a range of 175 to 250 amps. So this is a 250 amp thermal magnetic trip. You can see it's got 1, 2, 3, 4 adjustments on its thermal. That's the thermal setting, and the magnetic setting is a factor of what this is set at. Not 250 amps, it's a factor of what this is set at. And then there is an instantaneous value out here, which is not written in here, but there is one, and it will trip out. And it's based upon a bimetal system, and there's a little mechanical thing in there, but it's very coarse. It's a coarse type of trip. It's not what we're used to now with technology. A lot of our trip units are all electronic now, so they're much more adjustable, and such the word selectivity is what it's about. We can select more settings to get closer to the load and protect the network better. So in this one, this is a base level one, IO, IR, and ISD in the electronic version, and you can see there's a port and it can be tested. So these two here work together to set up the thermal, and then ISD is the short circuit, short delay. And then over here, we've got an advanced trip unit. Now there's only two settings in here, and that's IR and ISD. And to the right, which you can't see, is just a digital face. And you go in there and you set all the other parameters, all these other time delays, instantaneous, earth fault if you had it. So that's the way we've moved. There's less dials for contractors to go up to, and some of the more advanced stuff you're only just having a digital thing. So how can they work through that? They need guidance. We have tech support. A lot of companies do this, but if you're still applying all of these, then they're not going to be confused. They're going to be fine because they don't disappear. They don't change. IR is IR, ISD is ISD. So it doesn't matter what happens to the technology here, and it all becomes digital. Those parameters, those things that need to be set are still there. So the two other things that you need to know about a circuit breaker, really important, is ICU and ICS. ICU stands for ultimate braking capacity. That's the ultimate braking capacity of that breaker. So it's the KA of the breaker. So when you talk about a miniature breaker, what's the ICU? 6K, it's 10K. That's what it is. That's what ICU is. But that terminology is everywhere in every bit of literature you can think of. this breaker has to be able to see a fault, a maximum fault, prospective fault, to the value of its ICU value, in this case at 380, 415 volts, 36 kA. So that means it opens. Then you should be able to close it on that fault. It opens again at this point. That value is what it's saying it can achieve. But the reality is, though, some of them can't. Some of them are derated. You need to know this. You need to. We don't derate ours, but this is what they are. Some of them can be 50% of that value, can be 75%, even less than 50%. So just be aware of that. That's important. It's important because of what you've determined your prospective fault is when you do your design. You need to know this. But what's even more important, it's another figure here, is see where it says ICS. That's the service rating, or what I would call safety rating of the breaker. It's saying that this breaker can see the maximum ICU value, 100%. This is 100% because it says 36 and 36, but you might have 36 and 18 here, or 36 and less than 18 here. And that means open, close under fault, open, close under fault, open, and the breaker is still safe. So you certainly don't want to have a prospective fault sitting in the switchboard. We're all wearing PPE gear now, by the way. Gee, I used to be able to go up to switchboards and be able to go in there with a screwdriver, no problem at all, and say, look, this is wrong, and go in there and do it. I can't do that anymore. Not allowed to do that anymore. It's a no-no, you know. And I get that to a point, but generally speaking, switchboards are built pretty safely. But that's the way we are. That's the way we work now. That's fine. So I'm into safety. Don't get me wrong. I'm into full safety because things can go wrong. But what I do know, if I've got a rating on my breaker that's like this, I know I feel pretty good. I feel safe. But when was the last time that thing was operated? When it was put in, turned on, forgot about, 5 years, 6 years, 10 years, whatever, I don't know. And yet we think, yes.
Does the circuit breakers, if they're tested for OCO, does the finite number of trips?
Good question, and there's no simple.
I was going to say, do you want to repeat the question?
Oh,
Hello. If the circuit breaker is tested for OCO for the ICS rating, does it have a finite amount of tripping that it can handle before it needs to be replaced?
Yes, good question. The answer to it, it's more than one answer to it, but I'll give you the bad answer. The bad answer is, well, not the bad answer. The answer is, if it has seen this level of fault, it will need to be replaced at the end, because that's a massive amount of fault. And what you will find, if you looked at the circuit breaker, and I've seen plenty of breakers that have seen really massive faults, the carbon around it, if you open them up, the contacts, they haven't welded because they don't weld. Well, ours don't weld. But the damage is there. You can't reuse that anymore. But it's been safe at that time. But what do you know about this? Is that what the fault was when it happened there? Did it happen a lot further away and the fault was a lot less? So what the other answer I'm going to give to you on that is there are smarts now that you can get on breakers, on trip units, sorry, the trip units will give you contact wear. On large breakers, we give contact wear. And so we can see multiple faults on thermal because we're only talking about, you saw before, 130 to 150%. But on short circuits, we're doing multiple times. We're doing 10 times, 5 times, you know. So it's major. So the current that's going through there, the answer is I don't know, because every situation is completely different. But what you do know is that is safe and it's been tested through that scenario. And guess what? If it has, it will be knackered really, and it needs to go, and you need to replace it. Yeah, we need that. Another.
But the way monitoring, does it distinguish between the thermal or the magnetic? Or
yes, we do that as well. So you'll see in here, see this, just these lights,
yep,
red LED lights. We have ones that say this is a thermal fault, this is a short circuit fault. Yeah,
yeah.
well, that's been in electronics for quite a few years now.
Okay, yeah.
And,
but if it's like the majority of them, the normal one that you said earlier, the TM250.
TM, yep, they don't.
So you just have to. Yeah, okay, I'm with you.
The great thing, what I'll say to you, is that visual and smell give a lot.
Yep.
We don't even have to open a circuit breaker with the knowledge of suppliers, and even switchboard builders who have seen many of these over the years will know that this needs to be replaced.
Okay.
It's almost like we've had a few incidences in Auckland recently, when I say recently, a few years ago, where water has come into switchboards. What do you do in those situations? Do you get rid of the breakers? Can they ever be used again? No.
I used to work in a mining company,
yeah.
and we had circuit breakers from another company. I can't say the name. I won't say the name. And when we had these mobile skids.
Yes.
And so obviously being mobile, you have to add faults often. And then when we sent them through for refurbishment, they kept the circuit breakers because they look fine. And then as soon as they put it back into service, the first fault that they receive, they blow up.
Yes.
And then it's a warranty claim, and then everyone is fighting and everything. But probably the circuit breakers, I've seen more than their fair share of faults, you know.
Yes, yes, that's right. That's right. And yes, it is an application-based thing, and some protection devices are going to see more anger out there than others, and some will sit there for years and years and nothing ever used. Okay. But the main thing I would say to everybody is please open and close the breaker once a year, once every couple of years. Please do that at least. You know, when you're having those service times, that industry should just, it should be a thing that we should be telling everybody. It should be written down somewhere. It should be something that has to be done as part of the maintenance program. And it's an important thing to do because when the time comes, you never know when that time's going to come. You want it to operate. So, yeah, and you don't know. Okay, so I'll move on now. So thank you for your question. That was great. So this is really sort of probably the start where we're going. Selectivity, which is effectively discrimination, the word discrimination that we know. So this is a good definition of it, if you don't mind me reading it. Selectivity is achieved by overcurrent and earth fault protection devices. So let's say overcurrent, because earth fault can be dealt with, earth fault relays, etc. If a fault condition occurred at any point in the installation, is cleared by the protective device located immediately upstream of the fault, while all other protective devices remain unaffected. We call that total discrimination in the past. Now we call it total selectivity, but this is our goal. We don't always achieve this. We don't always necessarily have to have that, but it is something that we want to aim for. And this is where we can guide you through where you can make subtle changes within the protection device selection, within the protection device selection of not just the breaker, but also the trips and the way you set them. That's how you achieve selectivity. And sometimes even then you will fail because it's just not possible, but sometimes it's not necessary either. I can give you some examples of when it's not necessary, but yeah. So this is really, well, this is what I've said, it's replaced by this, and this is what we're after, improved continuity, okay? So those are the three faults that we're looking to do something with, and we can, what we call, it's a term that we call for two breakers is partial discrimination. So we can get up to a value. So as suppliers, we have tables that will tell you that if we don't have total, we'll have a discrimination value up to something. And you'll see that in the software tools as well. And that often that up to level is pretty low. You just think, wow, that's not very good. But who knows what your fault's going to be? Who knows where that breaker is in the network in relation to what the prospective fault level that you've actually analysed is. So it might be fine. So, or it's very highly unlikely that you're ever going to get a short circuit in this particular circuit for one reason or another. And one of them I can give you is power factor. Power factor. Power factor is important. Is it necessary? Yes, it's necessary for your power bill, but at the end of the day, is it going to cause any other issue in your network? Maybe a little bit, could do, because you can get a little bit less, particularly if you're fully loaded up on your transformer, but maybe not. And so you might find that that's okay. So partial discrimination is sometimes acceptable. Okay, so the standard, the ASNZS 947-2 is for circuit breakers, selectivity standard. So if you look at this statement on 2.1 is saying overcurrent selectivity is the coordination of two or more overcurrent protective devices, and such that on an incident of overcurrents within the stated limits, the device intended to operate within the limits does so, while the other does or does not. So meaning it might not. So this falls into that partial discrimination. They have to have a statement in there for that as well. They're not just talking, because we always say, oh, well, if there's no total, that's hopeless. Well, please don't think that, because it's not necessarily true. And then we have a statement there for total selectivity. Okay, so they have covered, which is nice to see that they've covered both elements. So just this is a way of looking at it. That's pretty obvious, isn't it? So I don't need to. It's very simple. You can see why that's total selectivity on this side, because this one hasn't. This one's open, this one's closed, and this one is both opening, A and B. But this is with a bigger network. And what's good about that is that final distribution breaker open, but all of these are all good. All good. But I can quite honestly say to you, this one here, if that it was a normal breaker here, and this one had earth leakage up here, we might find that this goes out, then everything goes out. So I'm just going to reinforce, don't put earth leakage in the main breaker, please. Please. We've been asked a number of times lately, and I'm just saying it's just a no. Right. I hope everyone's familiar with seeing these sorts of things, but there's lots of different graphics that you can find in those. These are in technical catalogs, they're in your electronic tools that you can go online with, and these are the things that you can spend time on. And I think over the years, we've tried to simplify it, make it easier for engineers and switchboard builders, etc., to be able to utilize these tools and see are they going to get discrimination between two curves or not. And so the ones that you need to look at are current, which is this part of the curve. This is IR, by the way. Time-based will always be short time, because it's a short amount of time. We can't graphically cover this one. This one is around test. Both these are around test, and energy is really high level short circuits. Like we were talking before about ICU and ICS, the maximum prospective short circuit that you might get, that's what this area is here. So we've got tables and graphs for all of those. This one here is quite a nice one to take away. So I think we're going to give this presentation out or whatever as well. Are we moving? Yep. This is wherever you see basic rules or general comments, please utilize this. Is a nice one. It just says between a thermomagnetic and a thermomagnetic, your target is to have something like 1.6 times the current between them. If you get that, you're likely to get selectivity, total selectivity. And for the short circuit side of it, needs to be a minimum of 2 times. Often it has to be higher, but at least 2 times. So as long as you apply that, and we've given other examples, thermal to electronic, and vice versa, and you'll see when you have electronic to electronic, see how the number's lower? That's probably to be expected, because the electronic trip units have got more adjustability on their trip units. So that's how we get better selectivity. And a good example of this is here. I'll just show this. So between these two, you can actually go on your calculator or something like that, but there is 1.56 times between these two in terms of the IR ratio. It's not 1.6. And because of that, if we went into our tables and you went into one of our electronic tools, it would say you've got partial selectivity up to 5 Ka. Well, 5 Ka sitting here on a 160 on a main board, you might find that's not great, not good. So we need to do something about that. We need to make some adjustment. We need to make some adjustment here, or we need to make some adjustment here. So the first thing, the most economical solution, if it is possible, is just lower this. And we end up with total selectivity. You can see how the curves have just come apart here, and now we have it. But you might not be able to do this. I know you don't select, I know most people don't select a 160 amp breaker or a 250 amp breaker, and it's fully loaded up to 250. We just know these things. So the odds are that you're going to be able to change IR. But if you're not, then you're going to have to do something about these two breakers if it's important to you that you've got total and not partial. Yeah, just to consider that. So I'll just go back there. This was current based. So it's the thermal part of the curve we're looking at here. Now we're going to look at the time based, which is this part of the curve here. So these are TMD trips. They're not electronic trips. They were the base level breakers, which you'd see everywhere. And you can see here it's 1250 amps ISD, and it's 2500 amps here. And I'll go back, and that's actually giving us total between these two, because that is 2 times. Remember we said 2 times? And you say, well, where did you get those figures from? Where do you get those from? Well, because they're thermal magnetics, there is a fixed instantaneous value is another way of saying it, but short delay time for those breakers. But when you go into electronics, they can be different figures. But for thermal magnetic, there is a fixed value of a current that it will trip out in, and that's 2 times. So we know it's okay. Right, now we're going to have a go at this. This might be a bit tricky, so I just need Moomin to get involved. What we're going to do is take you through an electrical online tour if you haven't been there before. So I'm going to go pretty quick with this. So if you put in electrical calculation tools, you're going to get this area here, and it comes up with electrical calculation tools, Schneider Electric New Zealand. Click on that, which is great. So we're high in the rating there. And then when you get in there, just tab down a wee bit and you will find Access Electrical Calculation Tools. Click in there. This is important for me because I'm not so good at this. Some people are very fast at it. And it's just working its way through. So we're live here online, and you would have been, so we've got a Schneider connection, but you need to log in yourself. So once you've got a log in there, you only need to register once and you can access in and out of there. Once you've done that, it's going to take you into a selection of tools. So come down and we're going to go to check selectivity, but there's other forms of tools, cascading on its own. So let's choose some breakers. First one we're going to choose is an NSX 400, I think. Yeah, 400N. And then we're going to change to a 3-pole. We're going to change the trip unit to a 2.3. That's a base level electronic trip unit with 2 protection settings. Select another breaker downstream. Compact NSX, this time 250. And 250N. Change the pole rating, and we're going to put in a thermal magnetic trip. And we're going to select one more. So we're going to have 3 levels, this time a 100. So you can see it's relatively quick. I don't know if you've used it. I hope you have. If you haven't, you have a play around with it, particularly changing trip units. You'll see some differences. And we check selectivity. And we're going to get a result here, which is not going to be 100% for us. But we've got selectivity limit up to 4,800 amps. And as we say, between the 400 and 250, but total between the 250 and 100, which is understandable because we're over 2 times there. So what are we going to do about this? What can we do? So in this situation, I'm advocating, just through general knowledge, is change it to a 630. But the reality is, because it's the same frame size, it's a great thing. So if it's physically the same frame size, we can slot it in the same place. With a 630, we can still adjust it to the 400 or less than 400 to what we need in terms of our IR setting. Yes, it's cost us a bit more, but look what we've achieved. If we go in there, we've got total selectivity for everything. So that's our goal. If that's our goal, then there's the answer. Sometimes the answer is not always being able to adjust the current to get there or change the trip unit. You won't know until you have a look. You can look on tables. Sometimes it takes a lot of time and effort to go through the tables because there's pages and pages of them, you know. I use them occasionally, but I'm just saying this is a nice way of doing it. I think that was the end of it, wasn't it? Yeah. Thanks, Levin.
Oh.
Okay, hope you got some value out of that.
Me again. In terms of the short circuit, where you're in the LI portion of the curve.
This one here, II.
Yeah. Let's say, for instance, that graph.
Yes.
You're in the fault level is, let's say, 5,000.
Yes.
So you have your discrimination tables. So when there's a fault, obviously all of them would want to operate at the same time. But I think the previous slide mentioned that
I can go. I'll go back here. Yeah.
Yeah, because of the arc resistance, there's not enough energy to trip the upstream one.
That's right.
But that comes from basically the discrimination tables, which was based on empirical testing, I would imagine.
Yes, you're ahead of me because that's in some of my other slides, but you're right. There is between devices when we can't show it graphically like this because it's very fast time. We're talking milliseconds that these things happen. Sometimes up more than that because we know that boards can be built and requested for withstand of half a second, 1 second, 3 seconds, which is massive. 3 seconds. You don't want that, but there is some like that. But this situation is that has to be done under laboratory test. As a supplier and a manufacturer of circuit breakers, we need to say that these two together can work such that they can work with the fault that you're talking about.
But let's say you're a contractor and you're on a brownfield site, and you are installing a panel. For argument's sake, you're installing a new MCC panel from Schneider.
Yes. And
you're being supplied by an ABB upstream circuit breaker.
Yes.
What would you do in that case?
Well, I would talk to the odd electrical engineer who says that they use a product called, I think it's called PowerTag. But no, not PowerTag, PowerCAD. PowerCAD, and it has multiple brands that you can compare for discrimination or what we're now calling selectivity. And I would say to that is that you can accept that between on current, on thermal, on short circuit, no.
Yeah.
So all you can do is on the basis of what you understand. If you saw a supplier with their two brands, one brand above and a different brand below, you can say, oh well, I must be able to assimilate that with these two different, with these two different breaker brands. And I say no because it's not tested. But you would say, oh, it's probably okay. but the technology are different.
Yep.
They're different. So there's no guarantee, but
I guess it comes down to the chances of it happening.
yes.
Because if that's a large backbone and it's static, that'll never change often.
So all I say as a supplier, all we say as a supplier is that if you have a chance to keep the same brand all the way through, please do so. If you don't, for some reason or not, then you have to take that in consideration under short circuit faults, that you really don't have a full guarantee. But if you had a 250 amp upstream and a 100 amp downstream, which I've already said, it's 2.5 times, you would expect every day of the week that there'll be no problem with that. So, and you'd have two different brands, as you say, every day of the week, you'd have no problem with that. But the reality is I'll put my hand up and say, I'm not going to guarantee it because I'm the supplier of the A device and the other suppliers of B, and he's going to say the same. When something goes pear-shaped, you have no guarantee.
No.
So keep the brands the same.
It sounds
just
like
make sure that they're flowing green. That's all.
Yeah, it sounds like a tender exclusion.
Yeah, but yes, good question, because it is true. It's a question that it's the things that I've put out there before. Good, it's good. Test. It can only be done a test when you've got high short circuits, and we're talking about very short periods of time, like milliseconds. You can't do it any other way. Yes, that's right.
So basically, that online tool is a graphical representation of those tables.
Yes,
basically.
yes, it is. Absolutely, it is. Yes. So it's taking the pain away from you, going through that catalogue and flicking through the pages and finding the right table. And thinking, gee, I think I've got it right because that number looks better. And then you realise you've actually picked the wrong table. Whereas you're not going to get it wrong with this, are you? You're selecting the breakers there. So that's what I like about the electronic side of it.
Okay, thanks.
Yeah, cool. And this really is a good question because it brings us into this one. So we looked at current, we looked at time, but this is energy. And this is that instantaneous side of when we're getting very, very high short circuits. So you need to compare, and as a supplier, we do that around that instantaneous value. This is the high short circuits. These are the three-phase voltage short circuits that you can get. There's massive faults. So you've got to know that the breaker can withstand it or not. And what we have is what we call is this let-through energy that can be experienced, and it's very, very high. So we have tables like this. Not a lot of people look at these. That's very rare. We're able to determine it through the softwares anyway, what you need, and we're recommending this breaker with this breaker, except the coordination tables will tell you that. But these are what the breakers are able to withstand under very high short circuit values, and we have curves for them. And they must be, and I'll just say over here, the selectivity tables, and they must be tested. And this, going back to your question before, when two breakers are not tested, only current and time selectivity is able to be used. Even with their own breakers, because we'll say to you, well, two breakers not tested. Well, we have new offers coming in all the time, and we're not always testing them straight away. We don't see the benefit maybe in this offer with all of these. Generally speaking, we like to test as much as we can, but not everything we do. And if we can't give you that, we say, well, we haven't tested between those two devices before because we hadn't thought that they would ever be used that way. But industry always has a way of finding that they do, and they say, no, that would be perfect for us, and we'll do that. Well, see, there's no test for that for this level of concern, which is energy selectivity. So we want in the energy ones, this is the downstream device in relation to the upstream device. This one can't operate. It must be higher in terms of its energy capability than the downstream. And yes, we give details on that. And this really leads on to the table that you would see. We have pages and pages and pages of these things. So this is just a little example I'm looking at here. NSX 160 can be a 100 amp trip with it. There's the IR setting. And downstream, we've just got an IC60, which is a miniature circuit breaker, 50 amp. And if we have a look at that, that is our partial discrimination level up to 0.8 kA. So it's not even 1 kA. You know, that's a 6 kA device, but really, and if we see a fault greater than that, it can trip out the upstream breaker. So that's not really ideal, is it? So how do we overcome that? Well, just go up one size straight away. We can adjust this down a bit because it's a thermomagnetic, but a thermomagnetic, you've only got 0.7. So 0.7 times 125, we might get there, or we might not. So then we get into changing these to electronic trip units and so on. So you have options, you have a way through the design somehow. Now this brings us to fault current limitation. So fault current limitation is what the circuit breaker is doing. It's limiting the fault. That's what we want it to do. And what is a fault limiting breaker? Well, most of the time it's the multi-case circuit breaker. Sometimes it's the miniature, some of those larger miniature breakers. But the limiting capability of, and I'm just going to say it because I've kept away from brand the whole time, the NSX range, the NS range before was rotoactive braking capacity on each of the poles individually was painted for so long, and now it's copied now. But I'm just saying it's super famous, and the ability to limit the fault on downstream was tremendous, and it was because it was able to get a breaker that was going to act for the first time as fast as fuses. Well, not quite as fast. Fuses are still, but we're talking fractionally. The breakers today are very, very fast. So what this diagram here is really showing us here is this is what can happen if you don't have a fault limiting breaker. You can see a prospective fault level peak of multiple times the prospective fault itself. So it's a massive amount of current. We don't want that to happen. Why? Because it's going to affect cables, insulation in a thermal sense. It's going to affect the mechanical aspects of it. You've probably seen videos of some of these short circuits. You've seen videos of switchboards being tested in Sydney, etc., and you've seen the big bangs, etc. They're put through, the switchboard is actually being put through, through a lot, but it's the protection devices that have got to be able to withstand it as well within that board. Well, a lot of deformities can happen. The buzz bars can start to twist and stuff if they're not supported correctly. That's what they do on the switchboard in those tests. So being able to limit the current quickly limits that damage that can occur wherever this is happening, in the main switchboard, in the DB somewhere, to the cables that are connected. So the quality of the breaker, the fault limiting breaker, is very important. So if you can do that, then you can go another level, and this brings us into cascading. Because of that principle alone, the ability of that breaker, we have been able to introduce a concept that has always been around, cascading or backup protection, in the fuse world. Before circuit breakers even existed, we had fuses where the upstream was bigger and hopefully sat there, but if it didn't, it might pop. But we didn't end up with selectivity or discrimination. But with circuit breakers, we were able to do both selectivity and also reinforced braking capacity. So this is a technique using properties of current limiting, what we just talked about, to permit the insulation of the downstream switchgear cables and other circuit breakers significantly lower performance than otherwise necessary. So that means by having a good selection breaker upstream with that ability, we can put in a lower value fault level breaker downstream. This is what we were able to achieve. Of course, can't do it. We're talking about big energy here. It's got to be tested. It has to be. Compatible switchgear combination must be provided by us, and energy let through must be less than the energy of the downstream circuit breakers. That's that energy information that we were telling you about. They're really important information. If we want to apply cascading, we've got to be able to do all this, and that means this table. And this table is the money table. The money table means that if we select one of these, we can enhance the braking capacity of what, it doesn't say what that is, but I know what it is. It's a 6 kA breaker, up to 25 kA. as long as we're using this breaker, this fault limiting breaker upstream, as long as we're doing that, then we can achieve this level. And we've pushed this really hard. We struggled in the early days of cascading, of the new technology coming in 20 years ago. It's terrible. I shouldn't show my age, but 20 plus years ago, we were struggling to bring this principle across to electrical engineers, because electrical engineers know this is a prospective fault. We want a circuit breaker that can handle that fault. No, that's what we want. But we can do this. We can do this. We can do this. No. But we're going to guarantee it. No. But the industry has accepted it now because it's money. It's money, and it's real, and it's tested, and it can withstand it. So if that's the case, then that's good. And you can see here that was with a miniature circuit breaker, but here with this could be in a subboard somewhere, but the fault level is still very close to those transformers. So this is in the main board. This could be in a subboard, could be in the main board as well. But we've put in an F, which is only rated at 36 kA, but its capability is up to 70. So we kept the cost down. The size of the board and so forth can all be affected. It's a brilliant thing to use, and we promote it. And what I said really at the beginning, I think I remember saying to you that it was nice to see switchboard builders putting a lot more information on their switchboards, and they're doing it. I know a number of them. Some of my customers are doing it, and they just and we would suggest that you, as consulting engineers, say that this cascading is applying on this board. You need to do that, actually, because if you don't, and someone comes along and puts in a different brand here and does something else, that doesn't apply anymore, and that happens. So don't, it's a good thing that they're having that on there. I love seeing that. It's brilliant. This is a nice example of the potential faults that you can get. So I've got a 150 kA capability. It's a full limiting breaker here. We have a 25 kA breaker here, and we have a 15 kA breaker here. But the prospective fault level is higher than the ICU here. It's higher. In this case, no. At the source, at the beginning, you must have a breaker that deals with a fault at the top, because that's what it is. You've got nothing above it. Let's say you've got nothing, but you've got nothing. You've got no cascading happening above this. This is the starting point. So you must have the breaker for the prospective fault you've calculated here. Downstream, all this downstream stuff, this is where you have opportunity to make change. And there is another table. I just put this in here as well, just in case there was a question, but I've seen tables that are showing two values, not just the one. You remember the previous slide where it said, but there can be two. Most of the time they're the same, but sometimes they're not. So you can see here that the first number is the selectivity limit by cascading. So sometimes there is a slightly lower value, but most of the time in our tables, it's exactly the same. So I just wanted to point that out to you, just in case someone saw that. I'm not going to go through that one because I want to go straight to the design guidelines. Oh, that was okay, but I think I've covered a lot of the other stuff. So here, simple design principles. This is really, this bit here is about our product a little bit, but this bit is not. NSX 100 with a micrologic with MCCB RCBOs, and NSX 100 with 125 to RCBOs. Use that, but don't use this. But a lot of people might use this. TMDs do not provide selectivity. It's just what we know. It's just a simple thing. If you have this in your file, it's just you'll find that in the tool. But we come across this a lot. Our tech support team will come across this sometimes. So well, no, you don't have discrimination there. You need to change. Other arrangements, skip a rating. Skip a rating. So what does that mean? I think it's the next slide. This really tells it all. You can really see it here, except for one. But you'll see I've got 1,000 amps up here. It's 400 here. So between that 1,000 and 400, there's an 800, there's a 630. So we've skipped two there. So that's always going to be total. 400 to a 160. Next size down is a 250, then I say 160 total. So So whenever I go up to a drawing, whenever I see a consultant's drawing, it's so quick. It's not rocket science. You can, if you just apply this straight away, you said, oh, it looks like there's an issue there. Why is that like that? Well, we've got no choice. I often hear that I used to, when I was seeing consultants occasionally, I just said that they said, there's no way we can fix that. But there's always no way to fix something. You just got to, have a look. Could be a trip, could be something else. Or maybe what I said before, partial discrimination is acceptable. It's acceptable, so you don't need to worry. So this brings me to, hopefully, we've got plenty of time. Good.
Yeah, all good. Just keep going.
We've got plenty of time for it. Oh, that's great. So some of the key points. Selectivity improves continuity of service. Pretty standard, isn't it? Only the break immediately upstream, the rest of the installation unaffected. Key. Current limitation, reduction of harmful effects. Look at all the benefits. Fast acting, reduces stress on insulation, allows cascading effect, which we know is the money area. And upstream current limiting device boosts the performance of a downstream device. So that's the key there. And also value and footprint can be smaller often. Right. I went a bit quick there, but I just thought there will probably be plenty of questions.
Cool.
Maybe.
Thanks, Bruce. That was just as good as it ever was. You haven't lost it, mate.
Oh, thank you.
And any questions in the room? If not, we'll take some online, and that might prompt some. Okay. Hi, Bruce. What was your point again? Why circuit breakers need to be opened and closed at least one times in 2 or 3 years, aside from making sure it will still operate? Thanks. So that was back to your point of saying that we should always open and close them at least once a year.
Yes. Well, I should have been a little bit more specific on that. I would also say trip, because it's the trip function, because in multi-case circuit breakers, there's 3 parts. There's the trip position as well. And so when you open and close, you're mechanically operating the breaker, but it is really the trip one. And so some environments where these are sitting are shocking. Sorry, excuse the word, shocking, but they really are not good. So you are relying on the fact that they will be able to open and close. 95% of the time, you might be correct, but you might be wrong as well. So the open close is a simple process on a multi-case circuit breaker. On a ACB, we go into a lot more detail. There's arc shoots, there's a whole lot of things that we check out, and we can see that as a bigger breaker. But on multi-case circuit breaker, there's very little that we can do except for check the trip unit. So go into a trip state if it's an electronic one, and if not, at least open and close it. It's not a difficult thing to do, and at least you've got that assurity that it will operate.
Yeah, it seems like I bet the vast majority probably never opened or closed.
No, that's right.
Yeah, I was still thinking back, probably doesn't happen easy. When I was on the tools, I used to have factory fortnight, and during factory fortnight, all the maintenance was done. Every breaker open and closed, things were racked out, racked in. But I suppose in modern world, it's just 24/7.
Yes.
Not many offices which will be closed down for that sort of thing.
Yes, you're right.
Okay, next question. An observation only, there are instances of demonstrating total discrimination with the Schneider calculation tool, but the same arrangement in PowerCAD presents a discrimination error based on PowerCAD's interpretation of ASNZS 3000, e.g. achieving 2 times clear between curves. So that's possibly more of a PowerCAD related question.
So what was the specific question again? Sorry.
So an observation only. There are instances of demonstrating total discrimination with the Schneider calculation tool, but the same arrangement in PowerCAD presents a discrimination error. Now in brackets it's saying based on PowerCAD's interpretation of ASNZS 3000, e.g. achieving 2 times clear between curves. So I think that's more of a PowerCAD question.
It is a PowerCAD question, but I will just add a little bit of something in there as well, is that as a supplier, we have our own software that we rely on in terms of the testing and between our breakers, and I'm not going to knock any other software out there, but I will say with PowerCAD, is that we have supplied our logarithms for our breakers, and all suppliers that are in there have done that, but sometimes they change and sometimes they're not quite right, or sometimes we have a new offer. I'm not saying it's in this case it has happened, but we've in the past had the odd error for one reason or another, and it is this. And if you think about it, we're talking software here. We're not talking laboratory tests, which we can rely on. So we always rely on our two breakers. When we see it in a table, it's been tested, that's correct. In a software, we're not so sure when they're measuring against another brand, or if they're even measuring our two in there. We have to rely on that's working. We've worked with PowerCAD, my understanding is we have. Our Australian colleagues have done that.
Yeah, we use PowerCAD successfully with your product.
Australian colleagues have done it.
Okay, next question. Does cascading impact discrimination along with fault current limiting? I had thought that an upstream breaker limiting the fault to a downstream breaker had facilitated discrimination. Does cascading impact discrimination along with fault? Does cascading impact discrimination along with fault current limiting?
Well,
that's the first question.
Yeah, I'm just trying to figure that one out. So cascading is an added benefit and a technique that we can use, but it doesn't mean that we get selectivity or discrimination. We have to look to the tables that says that we have both. Some breakers that are tested together, we have both cascading capability and also selectivity together. Sometimes we just only can get cascading. So it's not always we get both, but we were able to do that with our particular NSX breaker, where we said you're going to get reinforced braking capacity because you use this breaker upstream, and you're going to limit the fault because you have that on the downstream device in conjunction with the downstream device. You're not going to change the fault. The fault is what the fault is, but you're going to get the two working together. But we're not going to say to you that you get both always. I don't know if I've answered that. I'm not sure.
I think you have. It's actually a colleague of mine, so I can ask him tomorrow.
Okay.
If that answer's not good enough,
that's good. No, that's good. That's good.
Corin, then you know who to call. Can you please explain the different parts of the curve for the let-through energy? It finishes at the word let-through. Can you please explain the different parts of the curve for the let-through?
I'm probably going to have to come back to you on that. That's the slide that.
I wonder if that slide that was at the very beginning. Now it showed all the.
No, it's the energy selectivity area. So we have curves on this, and on these curves of energy, the let-through, we have what that particular breaker is, and we have another one sitting underneath it and above it, and we can actually do measurement on that. But I can't answer that one, sorry, right now, but we can come back to them.
Cool. That was from somebody claiming to be anonymous. It's all good. Where are we at here? Hi, will the new ASNZS 61439 standard involve an update to the Schneider tool?
Yes.
That was a definitive answer.
Well, it's a major standard that we all have to comply to, and we've done a lot of work in behind the scenes here and in Australia. So
is that the new switchboard standard?
Yes.
Oh, right, yeah.
Yes.
Could embarrass myself there, couldn't I?
Definitely. We're supporting switchboard builders that need to do that. We have been doing that, particularly the ones that have been partners of ours. It's more of an issue in Australia than New Zealand, because a lot of New Zealanders, switchboard manufacturers have European switchboard systems, and they are all type tested, and they're driven around the standard because Europe and Britain, etc., have been ahead of the game and have promoted down this path. And Australia, New Zealand, South Africa, and the rest of it are moved forward. So there's a lot of bespoke switchboard systems in Australia, and there's some here too. There's less here. Some of our switchboard builders have had to go through the process of type test. Yep.
Cool, thanks. Okay, that anonymous is Rob Moore. Well, I won't mention his position, but he's our electrical lead at Becker. Good friend of mine, but hopefully he's after this now. I'm named and not named and shamed, Rob. Put a good word in with my superiors if this goes wrong. Okay. And that's all the questions online.
Oh,
Any
good.
other questions
Okay.
in the room?
Any more here? But it was. Thank you very much for your questions tonight. It's great.
Yeah. Well, that's everything. So big thanks to everybody who's turned up in the room, everybody online. How did we get online at the end? 65. Oh, that's a good turnout. And of course, huge thanks for Schneider for making it happen, and another massive thanks for Bruce
Thank you
for
very much.
putting the old
Yes,
magic
thank
on.
you very much.
Thanks, everybody.
Much appreciated. Thank you.